Good afternoon. All right, one last video for the week. Since we talked about the mathematical realities of the feasible regions last time, today should be a bit more concrete. I know last time we went into the very theoretical, very conceptual reason why the corner points of any given feasible region were really all we needed to focus on. It was actually a very nice argument, right? Once we got through the argument, it basically said, yes, in every feasible region there are infinitely many possibilities. But no, we don't need to find the value of the objective function for every point in that region because we can eliminate them wholesale. We can eliminate them starting with the interior points, then moving to the boundary points, which are not on the edges at the corners. And finally, we put a few arguments together and said, okay, if there is an optimal or co-optimal point, it will be one of the corner points. And so today, we'd like to develop that into the method of corners, which basically says we have a region. Let's find out what the value of our objective function is at the corners. And once we have it there, we don't have to do anything more than that. It's a really nice method. So today should be a bit more concrete. Let's take a look. The first example I'd like to work is this one. I just made this one up. Maximize p equals 3x plus y, that will be my objective function, in the following region. Give a couple of inequalities here. I've already drawn the lines to be somewhat accurate, but let's see. If we didn't have these lines, the way I would draw them is I would find the x and y intercepts for each one of these lines. It looks like 12, 0, and 0, 12. Would be the intercepts for this line. That's this one. 12, 0 and 0, 12. And for this line, the intercepts, remember to find the intercepts, I'm just plugging in x equals 0 and y equals 0. In this class, we're going to try to stick to lines which can be graphed this way. I know that if we have to, we can turn this into slope-intercept form, y equals mx plus b. But again, we're going to try to stick to lines that can be graphed using intercepts in this class. If I plug in x equals 0, then that just leaves y equals 18. That looks to be too far up to my picture. And if I plug in y equals 0, that gives me 2x equals 18, or dividing by 2, x equals 9. So that would be this point here, 9, 0. If I followed this line up, I would be able to find 0, 18 up here. But because of the shading that I'm about to do, I don't actually need to find that point and mark it on my graph. When I'm doing my shadings, x plus y is less than or equal to 12. I'm going to use 0, 0 as my test point. Plugging in 0, 0, it makes it 0 plus 0 is less than or equal to 12, which is true. So we shade in that direction. Plugging in 0, 0 to my blue equation gives me 0 plus 0 is less than or equal to 18. So we shade in that direction. And what we end up with is a feasible region which is shaded for both the red line and the blue line here. We're going to see this quite a bit, this sort of region that's tucked in next to the origin. And there's a reason why we like regions like that. They have a lot of nice mathematical properties. We won't have to go into them for this class, but most of the time whenever we see these regions, they will be this one. Or they'll be exactly the opposite, this one which goes away from the origin and extends out towards infinity. We'll see one of those later today in the video. So here's my feasible region. I want to find the maximum value of p inside this feasible region. And according to my arguments from Monday, none of the points matter except the corner points. So I'm going to make a table of my corner points. 0, 0 is technically a corner point. It won't be the maximum usually, but I have to put it in my list, right, because it can't be eliminated. I've already found two of the corner points, 9, 0, that's this one here, as well as 0, 12, that's this one up here on the top. But there is one corner point here, I do not know where it's at. Where's this corner point at? Anytime we have the intersection of two lines, that gives us a corner point, and one that we might have to solve for. The intersection of two lines was a system of equations thing. So let me take the equations for those two lines. X plus y equals 12. Remember, the equal sign is the line part. The less than is the shading part. We don't care about the shading part right now. I just want to find the intersection. And 2x plus y equals 18. Doesn't that look like a problem that we've already solved before in this class? A couple of weeks ago, we solved systems of equations. And we could do that any way that we wanted to. We could do that with Gauss-Jordan elimination, if you wanted to work with matrices. We could do that with substitution or elimination. Because this problem is so small, and it's already got a y equals or an x equals, I'm going to do this with elimination. So let me multiply everything in the first equation times -1, which would give me negative x minus y equals -12. 2x plus y equals 18. When I do that, the y values would cancel out. And when I add these two equations together, which is how elimination worked, that would give me x equals 12 minus 6. Yeah, that would give me x equals 6. This one is short enough that elimination is feasible. I know a lot of our problems will be a little bit longer. We'll have to do them with the Gauss-Jordan method, matrix methods. This one was a bit simple. And so, wait a minute, that gives me the x value. What about the y value? I think I need to plug this back into my original equation to find that y value. I'll start with the first equation, since that one's pretty easy, right? If I had to plug it into the second equation, it wouldn't be bad. 2 times 6 plus y equals 18. But from that equation, I can see that the y value should probably be 6 as well. 6 plus 6 equals 12. 2 times 6 plus 6 equals 18. So sometimes you will have to manually find that corner point. I saw in the forums this week, someone asked, hey, why is this corner point wrong? It looked very close to a whole number intersection, but it wasn't actually at that whole number intersection. It was at a fraction very close to that whole number intersection, but not at that whole number intersection. So be careful. Right? Reading your intersections off of a graph is a bit tricky and can sometimes lead you astray. Even if it's a very simple method like elimination, I still would suggest finding those intersections algebraically. So here's my list of corners. These 4 points are the only 4 points which could contain the minimum or the maximum value of p, my objective function. All I need to do now is plug those points into the p function and see what the p value is. So if I plug in 3 times 0 plus 0, here p equals 0. I guess unsurprisingly, right? If I don't have any x values or any y values, I won't have any p either. Plugging in 3 times the x value 9 plus the y value 0 tells me p equals 27 here. P equals 3 times 0 plus 12. The p value here is 12 at 0, 12. And p equals 3 times 6 plus 6, 24. So based on these 4 p-values, if I wanted to find the maximum p-value, here it is. The maximum p-value is 27. And it occurs at this corner value, 90. P equals 27. And I like that example because some students always get this idea that the maximum value will always be at that middle corner point that's kind of floating there in space and never at the edges or the origin. That's not always true. We have to plug in the numbers to figure out where it actually is. And if you wanted to get out your, do you remember from earlier in the week we had our ISO profit lines? That would be roughly it'll be a steeper angle. It won't be 90 degrees, but it'll be a steeper angle. And so the slopes of those ISO profit lines would follow this steeper angle. I'm not sure it's exactly 81 degrees, although I can check that for you really quickly. Give me my calculator. It's a little bit of trigonometry. You don't have to do that in this class. It would be 72 degrees. There we go. So here's the ISO profit line through 0, 0, and I can see there are better points, right? Higher values would be farther away from the origin. Here's the ISO profit line through 0, 12. There are better points than that. Here's the ISO profit line through 6, 6. There are better points than that. Here's the ISO profit line through 9, 0. And I'm going to move to the other side of the ruler so you can see how, do you see how through 9, 0 there are no green points left that I could move to, which are better than 9, 0. That's why I had to take the time to draw this picture accurately, or at least mostly accurately with the angles and the ruler. We can really only tell that if we can trust the relationships between the lines in our picture. Most pictures that I draw in this class are kind of back of the envelope. The lines are roughly in the right place, so I can't really trust them to display the correct angles. So I drew this picture to more exacting standards so you could see me sort of move around this imaginary isoprofit line, right? And the farther away from the origin, the better it would be, right? The farthest away from the origin I can go is this 0.90. And so we get a little bit of that geometry as well. Next week when we start working with what's called the simplex method, we really won't be able to see it using the geometry anymore, but the ideas are still there. I still want you to have this idea that we're operating under the same assumptions. We'd like to move to a better point if there's one available. That kind of informs the simplex method next week. Let's work on a word problem. This is directly off the homework. It's going to maybe be different numbers than yours because the numbers are randomized. Here's my version. Oh wow, it's a long one, but that's okay. Right? There's plenty of these. If you bought the older version of the textbook, you know, you can get older versions for really cheap. But if you bought the older version of the textbook, here's mine. There's plenty of word problems like it in the textbook. And there are some like it if you look at the links. Like I believe I've linked to, it's a free textbook, but I believe there are still word problems in that textbook as well. Here's the one from My Open Math. It says, a furniture manufacturing company is making dining room tables and chairs. A table requires 9 labor hours for assembly and 4 labor hours for finishing. A chair requires 7 for assembly, 1 for finishing. The maximum labor hours available per day for assembly and finishing are 375 and 145 respectively. So 375 for assembly, 145 for finishing. Write a system of linear inequalities that represents this situation. Ooh. Let's go back to our guidelines. Remember, we said before that whenever we're writing these word problems down, every choice is a variable. And every restriction is an inequality. So let's take a look at the different pieces of information that we have here. So I know I've got dining room tables and I've got chairs. I've got labor hours for assembly and labor hours for finishing. I've got maximum number of labor hours. That looks like a restriction to me. Do you see how, because this sentence tells me a restriction on the number of labor hours that I can use, that sounds like a restriction to me, right? I'm going to put labor hours for assembly and a labor hours for finishing. I'm going to put those in the inequality category because they're restrictions. And the number of dining room tables and the number of dining room chairs, it looks like I get to choose those things. Right? And based on the choices that I make, that tells me how many labor hours I'm using. Right? And so you see how the restrictions can sometimes be indirect restrictions. So I can't make 500 dining room tables, for example, because every dining room table requires 4 hours for finishing. Right? So I would have to have 400 hours available, and I don't have that many hours available. And so it's an indirect restriction, but it's still a restriction. I am allowed to choose tables and chairs. So it looks like those things will be variables, and labor hours, those things will be restrictions. Oops, excuse me. I said before that if I pull up my on-screen keyboard, it doesn't do that anymore. So the directions tell us to use, and this is a bit of cheating. You won't always have the directions to tell you this. But it tells us to use X for the number of tables and Y for the number of chairs. So it kind of told you which variables to use in the problem. You didn't have to decide how many variables there were and which variables you would use. I'm guessing it's really hard to make my open math problems that are so open-ended that you have to make those calls on your own. If this were an in-person class, it would be no problem. I would just give you the test and you'd have to figure that stuff out on your own. I'm not saying there won't be problems like that. Right? We could have a test which is partially print out and then turn in manually, not my open math. I haven't made those questions yet, but you never know. Maybe they'll happen. So let's see. I'm going to use X for the number of tables, just like it told me to, and I'm going to use Y for the number of chairs. So these restrictions need to be written in terms of X and Y. So let me start with the number of labor hours for assembly. How many labor hours do I use for assembly? Let me go back up to my problem. My problem tells me that every table requires 9 hours for assembly, 4 hours for finishing. So if a table, which is X, requires 9 hours for assembly, 4 hours for finishing, it seems like 9X, that's how many total labor hours of assembly come from tables. And if I did the same thing for finishing, it would be, what did I say, 4? I'm sorry to keep scrolling back and forth so much. 4 labor hours for finishing. Okay? A lot of students will get this backwards, right? They'll write 9x plus 4y, right? It's all about the units here. Right? If x is the number of tables that you're making, right, then 9x represents the total number of labor hours of assembly that come from tables. And 4x represents the number of labor hours of finishing that come from tables. Right? If I wrote 9x plus 4y, those things would be different units. Right? So that would be labor hours of assembly plus labor hours of finishing. That's not the kind of restriction that I have. Right? I could have a restriction like that. Right? The total number of labor hours you have is blank. That might be a different problem, but it's not this problem. So I'm keeping those things separate. Let me look at chairs. Chairs require 7 hours for assembly, 1 hour for finishing. So that sounds like chairs are y now. 7 times y is the number of labor hours for assembly. And 1 times y is the total number of labor hours for finishing. 7y and 1y. Then very last, now I have the maximum labor hours are 375 and 145. So if that's the maximum I can use, that must mean the total of these two amount of labor hours for assembly must be less than or equal to my maximum, 375. And the total of these labor hours of finishing must be less than or equal to 145. And those are the things I would type into my MyOpenMath answer boxes. Notice how everything in this inequality follows this unit. Everything in that inequality is talking about labor hours of assembly. Everything in the second inequality is talking about labor hours of finishing. Right? So I know that in textbooks and in websites and in videos, they'll just start throwing numbers and letters all over the place. But to help you make sense of this, to help you get a better intuition for when I am supposed to be doing one versus the other, I like to tell students to label your inequalities. Everything in this inequality is talking about which restriction. Everything in this inequality is talking about this restriction. If you start sorting them like that, you can start double-checking yourself to make sure you're not accidentally mixing your units. Right? That way I don't have this weird mixing. This will be the answer that goes into this problem, by the way. But if I were to really continue this and start graphing this, remember, I have those extra inequalities that come from reality. We talked about those reality constraints last time. I can't make less than 0 tables. So this is a hidden restraint, which comes from reality. I can't make less than 0 tables, so I have to have x is greater than or equal to 0. Same thing for chairs. I can't make less than 0 chairs. This is a hidden restriction which comes from reality. And that's why I said I will very often not even bother to write those down at the bottom. So if I were being honest, I need all 4 of these inequalities to graph a feasible region. This MyOpenMath problem will only require the first 2, though. Those last 2 are usually implied. Sometimes they're not even written, but they are there. Practicing with your word problems is a good idea, as much as possible. I say that and then I move to a non-word problem. I wanted to do this problem, one, because it's a minimized problem, and we haven't talked too much about minimized problems yet. And I wanted to show you a feasible region which is unbounded, that is, it goes on forever. Let me grab a graph here. Now this graph, you see I'm just spitballing this graph. I can't rely on this graph using the ruler the same way that I did my other graph. If I had a piece of graph paper, I might do a little bit better. As a matter of fact, let's have a sheet of graph paper. You may not be able to see the grid lines too well because they're very faint blue lines, but I can see them a little bit better than you may be able to see them. And I'm going to use them to 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't think I need to go any farther out than 10. No. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to use them to get at least a little bit better of a picture here. All right, let's graph our lines. Let's see, to keep things a little bit easier, I will put everything for the first inequality in red, everything for the second in green, everything for the third in blue. These last two come for free. Remember, that just means stay in the first quadrant. X is greater than 0, Y is greater than 0. All right, let's graph some inequalities. Does this work? I'm not sure it will. Let's see. So if I plugged in 0, 0 for the first inequality, 36, so if I plug in x equals 0, that gives me 4y equals 36. So 4 times 9 is equal to 36. And if I plugged in y equals 0, that gives me 5x equals 36. 36 divided by 5, oh no, it's 7 1/5. Now that's a fraction. You could make that 7.2 as a decimal. It's not a whole number. So if you don't like seeing big nasty decimals like this, you could take this equation, 4y plus 5x equals 36. Remember, the line is the equal to part. The shading is the greater than less than part. You could move that 5x to the other side, minus 5x plus 36. And then divide everything by 4, using a little bit of algebra. 36 divided by 4 is 9. Then I could use the y equals mx plus b. Now I have the slope. Now I can actually get a pretty perfect graph out of this. The slope is minus 5 over 4. 1, 2, 3, 4, 5. Down 5. 1, 2, 3, 4. Over 4. And then use my ruler to connect the dots. Now my ruler is not going to be perfect because unlike a real ruler, my ruler has to stick to whole degrees. Real lines don't stick to whole numbers of degrees that often. So even my graph paper picture is going to be a bit fudgy. Right? It's not going to be perfect. But it's going to be pretty close. If you're making a graph, you could do better than this. So you always have that option, right? And by the way, sometimes even this option, putting it in a slope-intercept form, won't give you a very good, it'll give you a big nasty decimal version of the y-intercept, for example. Right? So there's no silver bullet any way you do this. I said the next one would be green. So 3y plus 2x is equal to 18. If I plug in x equals 0, 2x equals, 3y equals 18. Y equals 6. If I plug in y equals 0, 2x equals 18. X equals 9. Okay, that's not too bad. So 0, 6, 1, 2, 3, 4, 5, 6, and 9, 0, which is here. I've already marked 10, so finding 9 is easy. Grab my ruler, hope that it falls pretty close to a whole number of degrees. Again, not perfect, but maybe about as perfect as I can expect, given my technology. There we go. Connect those with a straight line. I can see that these two intersect, and it doesn't seem to be at a whole number intersection point. I did my best to make it work. It might be that whole number intersection point, but we'll see when we get there. Let me do the last one first. Plug in my x and y values. 2y plus 2x is equal to 16. I bet you this one's easier. Plug in x equals 0, 2y equals 16, y equals 8. Plug in y equals 0, 2x equals 16, x equals 8. So 8, 0, 0, 8. 8, 0, and 0, 8. I happen to know that that's a perfect 45-degree line, and so I can set my ruler to 45 degrees and make it work. You may or may not be so lucky. Again, the trigonometry, geometry part of it is not required for this class. Now, let me worry about the shading now. 4y plus 5x is greater than 36. I'm going to use 0, 0 as my test point. That's the easiest one to use, no matter if it's greater than, less than. The only time I can't use 0, 0 is if 0, 0 is on the line, and it's not on any of these three lines. So if I plug in 0, 0 to the first equation, 4 times 0 plus 5 times 0, is that greater than 36? No. So I shade away from the origin. For the second line, 3 times 0 plus 2 times 0 is not greater than 18. Shade away from the origin. Third line, 2 times 0 plus 2 times 0 is not greater than 16. So it looks like I'm shading away from all three of these lines. Which region shades away from all three of these lines? And it's out towards infinity. So, it's out here. I'm staying outside of all three of these lines. There is a corner point here. I'm gonna zoom in on you. Nausea alert. There is a corner point here. Uh-oh, don't do that. I don't know what this corner point is yet. Because I'm zoomed in so far, my pen is very thick. There is a corner point here. I'll label it when I zoom back out. Staying outside of all the lines. Oh, looks like there's another corner point here. Now I might be able to zoom back out and make sense of it. Staying outside of all the lines. And remember, the x is greater than 0, y is greater than 0. That means I've still got to stay in the first quadrant, so I can't cross over into the negatives. It goes in that direction, all the way out to infinity. So do you see how this entire region is shaded? That's a big region. And that's okay. Right? Remember, we don't care about anything other than the corner points. Oops. Let's decide what our corner points are. 0, 0 is not a corner point for this region. It looks like 0, 10 is a corner point. That's this one. And 9, 0 was a corner point. That's this one down here at the bottom. But the other two, which I marked when I zoomed in, here and here, they're not labeled. They're kind of floating nearby whole number intersections, but I don't know if it's just because I drew the graphs badly or if they really are at fractional intersection points. I need to figure out what they are. So I have two unknown corner points. The nice part, though, is that I know one corner point is at the intersection of blue line and red line. And I know the other intersection point is at the intersection of the blue line and the green line. That's going to tell me how to set up my system of equations to find these corner points. So let's scroll down. Let's find the intersection of blue-red. Let me go back up to the top. Again, I apologize for having to scroll so much today. So blue-red. So that would be 2y plus 2x is equal to 16. That's my blue line. My red line is 4y plus 5x is equal to 36. I don't need any of the other lines. Right, so this is a system of equations. Two equations, two variables. I can solve this using any method that I'd like. Again, I'm a bit like I could solve this with the Gauss-Jordan method using the matrices. We will have to do that starting next week, so might not be a bad idea to start practicing right now. But because I see that this is going to involve a lot of fractions, I'm a little bit lazy, so I'm going to get just a little bit farther on elimination because I know I can. Let me multiply everything in the top equation times -2 to make -4y minus 4x equals -32. The bottom of the equation stays as it is. Do you see how multiplying the top equation times -2 made it all cancel out very nicely for me? Like I said, we won't be able to rely on elimination forever, but it's nice while we have it. Looks like x equals 4 is the intersection. I can plug that back in anywhere. This equation looks simple enough. 16. Subtract 8. And then divide by 2. So it looks like this intersection point is at x equals 4, y equals 4. Sorry, I'll pause there for a moment. X equals 4, y equals 4. And I can see that it didn't look like this was at a perfect whole number intersection, but it actually was. That meant that my picture wasn't a very good picture. 1, 2, 3, 4. 1, 2, 3, 4. Uh-oh. Yeah, that intersection was way up here. That intersection should have been right here. The way that I drew this picture using my ruler didn't work out so well. So I already had marked that intersection point. It's just that the way that I drew it, it didn't work out too well. I don't think this intersection point, the blue line and the red line and the green line hidden under there, I don't think that's going to matter. But if you were paranoid and you wanted to find out, you could go and find that intersection point too. So this point is at 4, 4. It is one of my corner points. Let's find the blue-green intersection point. I'll write the green one first so I don't have to keep scrolling back. 3y plus 2x equals 18. That's the green. I'm going to have to scroll back anyway, because that was the green and the blue. 2y plus 2x equals 16. Blue. This is me finding the blue-green intersection. You want to do matrices for this one? Or do you want to coast by on substitution elimination for one more week? I'm lazy. Mathematicians are inherently lazy. We like to do it as easy as we can while we still can. We will very quickly get to the point where we'll have to do this with matrices, I promise. It's coming. Not today. Y equals 2. Oh, maybe this was a whole number intersection. Plug that back into the first equation. I guess it's the second equation now. Subtract 4. Then divide by 2. So this should have been a whole number intersection too. That's all right. Right? You can see graphing is an inherently imperfect method. Right? Even if we had a perfect graphing calculator on the computer, like Desmos, then it would help you get through this process faster. Yes. But if you use something like that, you've got a little bit more responsibility to show your work, right? Document your process. That's the most important thing. Document your process. That doesn't mean you have to do every step by hand, but it does mean that you need to document your thought process. Right? I can replicate your calculations all day long. I can't replicate your thought process unless you tell me what that thought process is. X equals 6, y equals 2. 1, 2, 3, 4, 5, 6, 1, 2. So it should have been right here. 6, 2. My corner point should have been 6, 2. And if your idea is, hey, I've got a graphing calculator, I'm going to use Desmos, I'm going to find all those intersection points so I don't have to worry about drawing these imperfect graphs, Professor. My ruler sucks anyway. I'm okay with that. Right? As long as you find the corner points you need to find, and you tell me how you found them. I've got 4 corner points, and I'm going to copy them and then erase all the stuff that I don't need, so that way I don't have to keep scrolling back up and down. I will scroll up just to find my objective function. So z equals 4x plus 3y. Paste in my corner points here, so I can write them down without scrolling back up. 0, 10, 9, 0, 4, 4, 6, 2. I'm going to plug them all in to each of my z values. 4 times 0 plus 3 times 10 equals 30. 4 times 9 plus 3 times 0. It's 36. Oh no. Yeah. I forgot my multiplication table for a moment. Excuse me. 4 times 4 plus 3 times 4. That's 16 plus 12. 28. 4 times 6 plus 3 times 2. That's 24 plus 6, or 30. And remember, I'm looking to minimize this value. The minimum value of z looks to be right here, at this corner point. 4, 4. So before I box in my answer, I need to make sure that moving in any one direction is not going to make it better. Right? The problem with this particular region, do you see how it goes forever in this direction? I'll use a green marker to show that. Because this goes forever, this region is unbounded. That's the word we use for it, unbounded. It goes forever. And so the way that I check to make sure that, because sometimes you'll have the situation where the maximum value doesn't exist, right? I'm going to check, does increasing x forever lead to a better result? Right? Here's my objective function. Does increasing x forever lead to a better result? Not really, because I want the minimum value for z. No. Does increasing y forever lead to a better result? Not really, because 3 times a bigger and bigger number will just be bigger, and I want a smaller result. So I always need to check that it wouldn't be better to go out to infinity. If I were asking you to maximize, the answer would be different. The answer would say, yes, it is better forever to make x bigger. Right? And so no matter which corner point you found was the maximum, and we did find a maximum down in the table, I would say, well, that doesn't matter because you could always increase your x value or increase your y value and be better. Right? My answer at that point would say the maximum does not exist. You will keep chasing it forever and ever and ever, but you'll never actually get there. It would be a D&E kind of scenario. But the minimum value, it does exist right here. So the minimum value of z is z equals 28, and it occurs at 4, 4. Whew. I know that's a lot. Even though we didn't talk about any of these sort of conceptual ideas today, I still think that this is a process which deserves your attention. It deserves some practice. So whether you're minimizing or you're maximizing, the idea is the same. Find all your corner points, and in and of itself, we saw that's not always easy. Once you've found all the corner points, make a big table, and then that will tell you the minimum or maximum value. The only thing we'll have to be concerned about after that is, well, when your region is unbounded, we have to go back to the top and make sure that going out towards infinity is not going to be better. Most of the time when you have unbounded regions, you're minimizing anyway, so it won't be better. But every now and again, it'll throw a trick question at you, and so we do have to keep on our toes. So today's video is a little bit shorter. By that means less than an hour instead of greater than an hour. So have a good weekend. I'll see you next week.